All right, welcome to the second introductory partial differential equations video. This is not going to have slides or anything. It's pretty much completely unscripted. I just want to talk a little bit about the physical motivation of what PDEs are, why we have these things, and like what's going on here anyway. If you have background in partial differential equations, if you've seen them in another class or taken a real math class on the topic, then you might gain something here, but ultimately the audience is first timers. So, with that, what I want to do is to talk about three different examples of partial differential equations that are very physically grounded and motivated, and just use that to explain some of the logic of how we think about these things. So, I'm not getting into the deeper theory of partial differential equations from a mathematical point of view. And it won't even be a how to solve these things. It's much more trying to just give some perspective of how to think about this stuff in a way that is physically motivated when you have physical problems. So the first equation that I want to start with is something that you may have seen in a simpler form in an introductory class, and that is the heat equation. So when you have the heat equation, you're talking about I have some solid, a rod or a bar or a plate, or whatever, a cube of stuff, and heat is allowed to flow through that substance driven by temperature differences. So what we need is we need a function, temperature of position and time. And we're just going to go straight three-dimensional on this. So we have a position vector. Really, there's a temperature as a function of x and y and z and time, which is to say that every place in our system that we're studying, each location has a temperature at every time in the time that we're performing the experiment, doing the measurements. So you have this truly four-dimensional system. People asked in the linear algebra stuff, are we going to do more than 3 dimensions? Yep, here it is. This is a 4-dimensional problem. We have 3 spatial coordinates and a time coordinate. And the way the world works, just in case you haven't noticed, is that things tend to change over time. But the way things change next, like the next step into the future, is determined by the state of the system right now. So the idea is that if we know all of the values of this temperature field everywhere in space right now at t equals 0, then 1 second later at t equals 1, we should be able to get new values for the temperature at every place in the system at every x and y and z if we know what all those things are, and we have a rule that governs how temperature changes. This is why we need a partial differential equation. It is differences, it is derivatives, it is changes in temperature that are going to drive how the temperature changes. And those are going to be fluctuations that change in space and in time. Things will happen as time changes, and how they happen depends on what the temperature is now at every different place. So what does this equation look like? Well, it's going to look something like this. There is going to be a derivative of temperature with respect to time. So temperature is going to change over time. And remember, this temperature is a function. It's not just a number. It is a function that has a value at every position in space. And that time derivative is going to be given to us by some coefficient. I'm going to call it A. It's a very clever name. And then this is where we get to the partial nature of things. It is going to be the second spatial derivative of the temperature in one dimension. Well, so we'll go to 3 dimensions very briefly here, but my typing is not perfect. Ta-da. Okay, so here's our one-dimensional version. And what this is telling us is that the way temperature changes in space, the difference between this position and that position, oh, it's that temperature over in the corner and it's this temperature where I am now, that tells you, well, physically, it tells you how heat is going to flow, right? Heat is going to flow from hot places to cold places. And that is what is being indicated by our spatial derivative here. So the spatial gradients, the change in temperature from one place to the next, determines where heat goes, because heat wants to go from high temperatures to low temperatures. And so that tells us how the temperature changes over time. This is the fundamental nature of partial differential equations in physical problems, is that where things are and what the value is at every different place tells you what happens next. So that was the one-dimensional version, but in reality, it is a three-dimensional problem. I put x vector up top. And so really, it is this guy. It's the Laplacian of the temperature. And this is where I go back to that vector calculus video where I said the really important nature of the Laplacian is not so much that it tells us curvature, although it does, but it gives us a sense of averaging. If the Laplacian here is positive, then that means that the temperature around the point of interest on average is higher than the temperature at the point of interest. And so as a consequence, well, if the surroundings are hotter than the place where we do the calculation, that means heat is going to flow into that place from its surroundings, and therefore the temperature will go up. And that's what we see. A positive Laplacian leads to a positive change in temperature. The A here is where we get all of our physical material information here. So just for funsies, this is the thermal conductivity of the material. So here's our material property, thermal conductivity. And then this is the heat capacity. Normally this is at constant pressure. We're just in atmosphere, right? So here's our heat capacity of the material, or specific heat to be more correct. And that's a material property. And then we have the mass density of the material, kilograms per meter cubed. So this A is the material information in the heat equation. The rest of it, the derivatives, are the general truth of heat goes from hot to cold. And then the quantitative extent, like the proportionality of how fast heat is going to flow, is given by the particular material that we're talking about. So that's one example, is the heat equation. Now, if we get a little bit spicier, then things change a little bit. What if we want to take that oscillator thing that we did previously and extend that? Because the oscillator was just one thing that was moving back and forth in place, like oscillating around some equilibrium position, like an atom vibrating back and forth around its lattice site in a lattice. But what if we just let vibrations move? Like, what if you had coordinated motions of the atoms in the lattice, and so there were these waves of vibrations traveling back and forth, and you need a wave equation for those things. And the wave equation is given by a different partial differential equation. Interestingly, it is still going to involve the Laplacian. I'm not saying that like all things are Laplacians. There are other equations out there, but a lot of stuff in the world around us, and this is a very deep philosophical question, is like, why is the universe governed by second order differential equations? I mean, we could talk all day and night and forever about that. It's very interesting to think about, but it does seem to be the case that regardless of why it is, a lot of the equations of nature are second order partial differential equations. So we're going to have, once again, a Laplacian here. And I am just going to define our wave function by f. It's just some function wiggling back and forth, waving around in space and time. So again, x, y, z coordinates and time. So now we've got, again, a four-dimensional problem, four different variables that are all orthogonal to each other. Unless we start doing relativity, but we're not going there yet. Okay. I'm not sure if that was a threat or what. But anyway, On the other side of things, this is going to look very similar to the heat equation, but it's slightly different in a very important way. The fact that the coefficient is 1 over, that's not the important way. That's just a matter of convention and units. This is going to be the second time derivative of the wave function on the right here. Like that. So here's our wave equation. This is the equation that describes the motion of waves. Usually, mostly. There's always an exception. But before you start being like, it's the heat equation. No, it's not. The second derivative here on the right is very important because it's not the direct rate of change. It is the acceleration of the wave value. Like, think about these things kinematically. First derivative is velocity. That's how fast it moves. But the second derivative is the acceleration. It's how fast the speed is changing. How much is the rate of waving at a particular place changing? And that is what's driven by this Laplacian averaging effect for the wave equation. But the way to think about solving this is a similar approach. You're like, okay, at some point right now at t equals 0, I can't believe I didn't get out an instrument for this. Well, it's too late now. I'm not going to get my sound set up. But like if I had some wave right now, okay, here's my wave. It's waving. Wum, 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 wum. Great. Now I know my wave function at every place in x, y, z at this time. What happens at the next time? Well, I need boundary conditions. I need to know not only what is the value of the wave everywhere, but I also need to know something about the first derivative because that's not given to me here. So in order to solve this equation, you can write down a general solution by doing clever math, but that's not going to help you solve any specific case unless you have the boundary conditions for that specific case. What is the wave doing, both in its current values and in its current derivatives? Because thinking about solving this, you're like, well, this tells me the second derivative. If I know the second derivative, I can integrate it to get the first derivative, and then I could integrate that to get the function itself, or the change in the function. But you can see that this is a process, that there's this real back and forth where you look at the spatial distribution of values, that tells you changes in time, and then time passes and the function changes, and now you have a new set of spatial values. The other thing that I think the wave equation is really nice for pointing out here is to remember that these things are unitful, that derivatives have units with them, and keeping track of those units is, well, first it's critical to getting the right answer, but it can also help you make sense of what's going on sometimes. So like the Laplacian here on the left, this is two spatial derivatives. So it's going to have units of 1 over meters squared. And the time derivative on the right, that's our second time derivative. So that is going to have 2 units of dividing by time, 1 over second squared. And so we have 1 over meter squared on the left. We have 1 over second squared on the right. How do you balance those things? Well, you need meters squared and second squared. And that's what this 1 over c squared is doing in this equation, is that c is the speed of the wave. And so that's what makes all the units balance out here. And if you're like, oh geez, I'm supposed to know the wave equation, but I can't remember if the c is on top or on the bottom, like do I multiply, divide? You can figure it out by the units. Do the dimensional analysis. Be good to yourself. It's a great tool to have. Use it. Okay. So this is waves. And then the solutions, no surprise, are sines and cosines and complex exponentials. In fact, if I take I'm just going to straight up give this away. We'll probably do it later in the semester, but whatever. F of x, I've lost the ability. It's going to be this kind of thing. So there will be some amplitude, and then it is going to be a complex exponential that looks like this. So the K, yeah, I'm leaning on those of you who took 242. If you haven't, I forgive you. So K is the wave number. That is 2 pi over, oops, K equals 2 pi over lambda. So this relates to our wavelength. And you're like, okay, that kind of, I guess, seems reasonable. Certainly it works for the units, right? X and wavelength have to go together because the units inside the exponential have to be nothing. It has to be unitless inside e to the no units. So we need the 1 over meters from dividing by the wavelength to balance out the meters in the x in the position. And then similarly in the time term, we are going to have a unit of seconds in the time. And so our frequency, our omega, needs to be 1 over time for those units to work out. And what happens now is, I'm just going to say this, I won't type it out, but if you're like, I want to know the velocity of my wave, how fast does it go? Like, how does that connect to this C thing in the beginning? Well, you can calculate that. And this is where you need to remember how to do calculus. I get you're like, guess you're like, okay, so I want to know dx dt, right? That's the speed. Like that's what we learned in physics 140 is its distance over time. Well, that should be something that I can calculate because I should be able to calculate some partial derivatives and do ratios and balance things out. So like that could be, let's see, I have a d dt in the bottom. So maybe I could, maybe I could put a df dt in here. Cool. And then if I want dx up top, then I need a dx df. And like that would work out, right? My df's would cancel and I have dx dt. And, you know, if you, again, go back to your Calc 1 stuff and kind of remember how to do these derivatives, then you can actually do this calculation and you get the speed of the wave. You get dx dt. And you can even kind of imagine it just from the solution that I've written, like, okay, if we take a time derivative, we're going to get an omega out front. And if we take an x derivative, we're going to get a k out front. But it's 1 over the x derivative, right? It's dx df, not df dx. And so you could kind of imagine that that is going to be something that looks, oh my goodness, like that. I'm just doing proportionality. I'm not worried about i's or pi's or whatever at this point. But just looking at the way the derivatives are, you're like, okay, yeah, differentiating with respect to t gives me omega. Differentiating with respect to x gives me k, something like that. And you look at the units of these things, it does work out. This is going to be units of, on top, that's 1 over seconds. And then on the bottom, this is 1 over meters. And so sure enough, if you, if you look at the proportionalities here, you're like, okay, I have 1 over meters on the bottom. I flip it over. And sure enough, we get units of meters per second, which is what the speed unit should be. So like, why am I going down this rabbit hole? First, I just think it's genuinely interesting, honestly. But also I really want to remind people that even though we're doing this crazy abstract stuff, like, oh my God, partial differential equations, 4-dimensional problems, the sky is falling, cats and dogs living together, like, it's okay. Do your basic thinking. Velocity is still dx dt. You can still take derivatives of things. You can still look at units. You know, this part of your toolkit is still with you. So use it. All right. Now, the third example that I want to give is a little bit different. And this is going to be coming from electrodynamics, from electricity and magnetism. And that is going to be one of Maxwell's equations. This is looking at electric fields and magnetic fields. And no, this is not just like some crazy pure physics problem. This is very, very relevant in materials. when we have electrical conductors and there are electric fields in these things because there's currents going around, we have electric and magnetic fields that are being generated. And so all of these power transformer applications of material science, thinking of the inverters that you need on your solar panels to turn that DC from your solar panels into AC for your appliances, like that's a lot of electricity in materials application, just to give one example. So on the right hand side here, we have the time derivative of the magnetic field. So this is a first order equation. That's nice. And this first order equation tells us that the way the magnetic field changes in time, again, look at your DDT term and think about, how do I step from this moment to the next moment? What happens in the next moment is that you're going to get some change in the magnetic field. So you're going to get some little, we take a tiny time step, a little infinitesimal moment, then we are going to have some change in the magnetic field, and that is going to be given by how long our little step of time is times the amount of change of magnetic field that happens in that moment. Whoa. Ta-da. I can type. Great. And that means that if we know the way the electric field is curling, we can talk about how the magnetic field will change. And you can then follow this logic and say, all right, here's my electric field. It's some function of X and Y and Z and time. And so at any given time, I can say, here's what my electric field vector looks like everywhere in space. Everywhere in space, it's got some value. It's pointing in a certain direction. And then you take the curl of that. So you do your del, your nabla operator, cross product with the electric field, and you get some result. That tells you then how the magnetic field will evolve at each point in space based on the curl of the electric field at that point in space. Okay, so those were 3 examples. That is actually longer than I intended to go on. I must have got real excited about units. So yeah, I hope you got something out of this. If you have questions, definitely let me know, and I would be more than happy to talk about this further. But hopefully that gives a little bit of physical motivation for how to think about these things, why we have different relationships between variables. And yeah, in the next really 2 weeks, we're going to be looking at techniques for solving these things numerically and doing stuff like this idea of time steps that I just mentioned at the end there in order to calculate small changes and keep track of them, add them up, and do all of the code development to work out these solutions. Okay, great. I'll see you in the next one.